Let's keep going here. Explain why ammonia NH3 is considered a Bronsted-Lowry base but not an Arrhenius base. So it's not Arrhenius. Okay, so it's not Arrhenius because it doesn't contain an OH. It has to contain an OH to be an Arrhenius. Okay, but it is Bronsted-Lowry because of the reaction we talked about earlier. You take NH3, put it into water. Now it's a weak base, so this won't happen most of the time, but it happens some of the time. And what happens is one of these protons from the water jumps over to the ammonia atom, or molecule rather, and makes it an ammonium ion. So it's NH4. That extra proton jumped onto that, makes it 4. Since only the proton came over, not the electron, it's now positively charged. It's called an ammonium ion. And then what you have left with the water is when you break off that proton, you now have just one hydrogen and one oxygen. So it's OH, and the proton that left, the hydrogen that left its electron behind, so it's minus. So again, that's the definition of a base. It has to leave an OH minus, a hydroxide ion, behind in the solution. Otherwise, it's not a base. So NH3 does that by breaking a water molecule in two, and then accepting the proton, and then leaving the OH minus in the solution. Okay, is water an acid or a base? The answer is both. And I'll give you a word that I didn't put in the slides, but what the heck. To be both an acid and a base, most substances are not, but it's called amphoteric. It means it can be both an acid or a base. Okay, so again, this is an example of where the water is an acid. It donated a proton to the ammonia and made that ammonium and made that hydroxide. So in this case, the acid acted like an acid, the water acted like an acid. It donated a proton over there. Okay. If, on the other hand, the water accepts the proton, and we've seen this reaction before, HCl plus H2O, now the water molecule is going to accept that hydrogen there and to become H3O plus Cl minus is the conjugate base. So in this case, water is a base because it accepts a proton from hydrochloric acid. In this case up here, water is an acid because it donates this proton over to the NH3 to make it NH4. Okay? So it can be both. All right, define a strong acid, and you can keep these answers short. It totally... Well, let me start. Since the H plus totally dissociate. Just to emphasize that 100% from the acid. So every time you put an HCl, just again, use that as the example of a strong acid. Every time you put an HCl in water, that hydrogen's going to break off and jump over to the water molecule to make it an H3O plus. Okay? All right, so that they totally dissociate. So name the 7 strong acids. So 3 of them are binary acids. There's HCl. There's hydroiodic. You can just write the symbols as I'm doing. There's hydrobromic. And then you get the oxy acids. There's nitric. There's sulfuric. There's perchloric. Again, that's an L, Cl for chlorine. And there's chloric, which just means it has one less oxygen. So those are the 7 strong acids. So every time you put one of these in water, the hydrogen, that proton is going to come off and jump over to the water molecule. Okay, keep going. Which of the acids will fully dissociate in water? All of them. That's not meant to be a trick question. It's just meant to emphasize all. So all of those will totally dissociate in water. Okay. That's the definition of a strong acid. What is the purpose of the pH scale? It's a user-friendly linear, so it doesn't deal with exponents, scale. Okay, so it's a user-friendly linear scale from 0 to 14 to indicate the strength of an acid. So 0 is strongest, 14 is weakest. That's acid. Okay, and that's what it does. Okay, answer the following. At 25 degrees just means it's normal room temperature. It really has nothing to do with the problem. So what's the pH? So this is the concentration of hydronium ions. So what does this mean? It means you have 4.87 times 10 to the negative 5th moles. Remember, that's a number of molecules or of these ions in a solution for every liter. So it's a concentration. How many of these ions, these hydronium ions, do you have in a solution for every liter? So, you know, dealing with this number is kind of messy. Scientific notation, negative exponent, all that. So the pH scale just gives a kind of simplified way to know how strong the acid is. So it's negative log of the concentration. And what you should try to do is kind of try to guess what you think the pH will be before you do it on the calculator. So if it were just 10 to the minus 5, just this, the pH would be 5. But this is 4.87 times 10 to the minus 5. It's 4.87 times stronger acidic solution. So it's more acidic because you're multiplying 10 to the minus 5 by this. So it's more acidic. More acidic means the pH is going to go down. Stronger acid goes towards 0. So if without the 4.87, 10 to the minus 5 is a pH of 5, then with this, it's going to be a pH below 5. It's going to head down towards 0. So, you know, who knows? Maybe it's 4.3, maybe it's 4.5, maybe it's 4.7. After you do a few of these, you'll get a sense of estimating. But it's going to be in the 4s somewhere. So let's go ahead and do this. So on the calculator, you hit the negative sign down here. Don't hit the minus, that's a subtraction. You hit the negative sign, then log, and then 4.87 times 10, and then the little caret sign, that little hat, is a exponent, and it's to the negative sign 5, and then you close the parenthesis, and you get 4.31. So you can see it's a lower pH, meaning it's a stronger acid, because you're multiplying it by 4.87 as compared to 10 to the minus 5, which would be a pH of 5. Okay, same thing for the rest of these. Okay, let's do this. Okay, try to estimate what this pH will be. So 10 to the minus 7 will have a pH of 7. But this is 6.1 times stronger than that. So it's a stronger acid, so it's going to head downward. It's going to head down below pH 7. And it's a pretty good number. It's, you know, closer to 10 than it is to 1. So we're going to say, I don't know, let's guess, 6.4, 6.3. Okay, so we'll do that one. So negative log 6.1 times 10, negative 7, close parenthesis, and you get 6.2. Okay? So there you go. Just do the rest of them silently. Sort of silently. Okay, so 10 to the minus 10 is going to be a pH of 10. This is only a little bit stronger, right? 1.12 is only a little bit bigger number than 1 times 10 to the minus 10. So it's going to be a pH below 10 because it is stronger than a pH of 10. It's going to go more toward the acid end, down towards 0, but not very much, not very much. So we'll probably guess 9.9. Okay. And there it is, 9.95, okay? I don't care how many decimal places you go to, it's not important. All right, So notice these pHs, they're all kind of nice, friendly numbers. They are decimals, but they're numbers between 0 and 14. They're all positive. So you're not dealing with this stuff over here. Okay, and that's the idea. Now this is POH. It's done exactly the same way, except you're finding out the hydroxide concentration in a basic solution, in a base solution. So we're going to write it the same way. Okay, do the numbers, negative, log. And that gives us 8.0. And let me write down, okay, these are pHs. And this is a POH. It's the concentration of hydroxide ions. Okay, right there. All right. Okay, this one's done the same way. I'll leave this one for you to do. Okay, exactly the same way. It is a POH. So done the same way, but it's POH. Okay, these three are going in the opposite direction. So what is the hydronium ion concentration when a pH is 5.8? And the way you do that, it's the inverse. Before we were doing logs, now we're going to do an exponential. And it's very simply 10 raised to the negative pH. Okay, so you just come here, 10 caret negative, in this case 5.8, equals, and now this is the trickiest part. You get that number, but you really should express that in scientific notation. So I'll go ahead and use all these digits. You don't have to, you can round, but it's 1585. So I'm going to write that down first. In scientific notation, this coefficient has to be a number between 1 and 10. So to make this number between 1 and 10, you'd have to put the decimal right there. 1.585 is between 1 and 10. So how many places did you have to move the decimal to do that? It's right there. So it's going to move 1, 2, 3, 4, 5, 6 places. And since this is clearly a number less than 1, it's going to be a negative 6. Negative 6 doesn't make it a negative number. It makes it a positive number between 0 and 1. Okay, so it's going to be times 10 to the negative 6. Okay, and that equals the H3O concentration. There it is. I wrote it right there. Okay, all right. Do the next one. Okay, so do that on the calculator, and you're going to see you're going to luck out if you have the same type of calculator. I'll show you why. Because it's 10 raised to the negative 10.11. That was the pH. And what you get is this time the calculator, because it was a small enough number, you would have had way too many zeros here. It actually gives it to you in scientific notation, so you don't have to convert it. So let's just call this 7.76. And then right there, very small type, it says times 10 to the minus 11. So that's what that's telling you. Okay, so that's going to be 7.76 times 10 to the negative 11. So it gave it to you in scientific notation. For this one, you had to figure it out, but it's okay. You should know how to do that. Okay, this one's going to be a OH concentration, a hydroxide concentration. So this is for a base. So it's a POH, but it's done the same way. It's 10 raised to the negative 2.04. That gives you is 10 raised to the negative 2.04. And that gives you 0.009, so we'll call that 9.12, because you got to put the decimal after the 9 to make it a number between 1 and 10. 9.12, and how many places did you have to move the decimal to get it there? 1, 2, 3. 3 positions, and again, it's a number between 0 and 1, or less than 1, so it's going to be a negative 3. Okay, so there you go with that. All right. This next series of problems is going to be on your district test. So it's kind of just an intuitive, which way is the pH going to go? All right. And so just remember, strongest acid, weakest base is a pH of 0. weakest acid, strongest base is a pH of 14. So the stronger the acid, the lower the pH. It's going to head down towards 0. So stronger acid is lower pH. Okay, so acid is added to a solution with a pH of 8. Well, pH of 8 is a basic solution. It's greater than 7, so it's a basic solution. So if you add an acid to that, you're going to make it more acidic. So that means the pH is going to go down. What did I say? Up or down? So use the word down right here. pH is going to go down. I'll just write that out. Down goes pH. Okay? Who knows? We don't know how far, but it's going to go lower than 8. We know that. Okay, now you can just write up or down. Okay, water is added to the solution with pH of 8. Well, water has a pH of 7. Okay, so if you put something with a pH of 7 in a solution that's a pH of 8, it's going to bring it down. Okay, another way to think of it is you're going to dilute this base solution. You're going to make it weaker, so it's going to be less basic. That means the pH is going to go down. But a good way to think of it is water has a pH of 7, so this is going to be pulled down towards 7 by adding water, so that's also going to be down. Okay, water is added to a solution with a pH of 3. That's not a strong acid, but it's a pretty strong weak acid. Okay, so that's a pH of 3. That's an acid. So again, you're adding water. So you're adding to it a pH of 7. So that means this is going to be pulled up towards 7 as you add water. So it's going to go up. That's all we're asking, up or down. So that's going to go up. pH is going to go up. Okay, strong acid is added to a solution with pH of 3. So as I said, pH of 3 is definitely an acid. It's below 7, but it's not a strong acid. A strong acid is either 0, 1, maybe as high as 1.5 would be a strong acid. So if you add, let's just say it's a 1. If you add a pH of 1, that's the strong acid, then it's going to pull this down towards 1. So it's going to go down. The pH will go down. Okay, finally, strong base is added to a solution with pH of 5. Well, this is definitely an acid. It's a weak acid because it's below 7. But a strong base is going to have a pH up around 12, 13, or 14. So that means it's going to pull this number up. So the pH goes up when you add a strong base. Strongest base is 14, so it's going to pull this number towards 14. Okay, and that's that. Okay, I gave you 5 of the same type of problems because you're going to see a problem exactly like this. The only thing different is the numbers, and you're going to see exactly like it on your test. And it's a little bit involved to do it, but at the first one seems confusing. By the second one, you'll kind of start to get it, and by the third one, it'll totally make sense, okay? Because you're doing the same procedure. So it's a stoichiometry problem. So what are you doing? You're doing a titration. A titration is you have a beaker with a known base that says known base. You know what its concentration is, you know how much you have. And what you have is this thing called a burette, and it has a little knob on it, a little nozzle. And what you do is you drip, drip, drip an unknown acid. So this is unknown. You might not even know what the acid is, but it's unknown concentration. We'll just call it unknown acid. What's going to happen is an acid molecule and a base molecule pair up. And when they pair up, they neutralize. So if we look at a reaction here, a strong acid, HCl, plus a strong base, NaOH. So that's a very strong base, very strong acid. They're going to produce a salt. Salt, S-A-L-T. And this happens to be the same kind of salt that you have at home in your kitchen that you put on food, although not all salts are that. But it just simply means a salt simply means a neutralized acid base. Plus the other thing that this is going to produce is water, and we know that's neutral. So a strong acid, strong base neutralize each other to produce this salt, which is neutral, and water, which is neutral. So notice it takes 1 acid for every 1 base to neutralize. It's a 1-to-1 pair up. It's like dance, okay? You got 1 boy for 1 girl, 1 boy for 1 girl, 1 boy for 1 girl. Okay, so when they neutralize, when you finally get these to neutralize, there's this magical kind of solution called an indicator. And it's really kind of neat to watch, because as you're dripping this acid into the base, both of them are clear. They look like they could be water. Okay, this is clear and the acid dripping in is clear. And then you put just a drop or 2 of the indicator in this solution and it still looks clear. But as soon as they neutralize, and how this works you don't have to worry about, as soon as the acid and the base neutralize, you've dripped in exactly as many acid molecules as there are base molecules already in that container, then that indicator turns bright pink. And there's other colors it can turn, but pink is one of the more famous ones. And it's really neat to see. You know, you got clear, 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 you put 1 more drop in and bam, all of a sudden it's bright pink. That means you have exactly as many acid as base molecules. Okay? So that's what we're doing here. So the problem says 30 milliliters of an unknown acid. So you know how much you had to put in, but you don't know how concentrated it was. So you got to figure that out. Is neutralized with 10 milliliters of 0.2 molar sodium hydroxide, which is a base. Okay, so to do this problem, you have to realize that 0.2 molar sodium hydroxide means 0.2 moles, remember what molar means, of NaOH, that's sodium hydroxide, for every 1 liter of the solution. Okay, so you notice that molarity is defined as moles per liter. Okay, we did that back when we were doing solution stoichiometry. Well, notice that these volumes are in milliliters, this one and this one. So the first thing you have to do, they could have made it easier and given you these in liters, but generally in a chemistry lab you are doing them in milliliters. So we're going to have to convert these two to liters. So that's very simply 30 milliliters. And you got to remember the conversion. There's 1,000 milliliters per liter. So I want liters on the top because I want to convert to liters. And on the bottom I want 1,000 milliliters because I want that to cancel. So milliliters cancels with milliliters. So you have 30 divided by 1,000 and that equals 0.030 liters. That's how many liters 30 milliliters is. Now you'll notice a little trick here. If you had taken the 30 and just slipped the decimal over 3 places to the left, 1, 2, 3, and put the decimal there, put a 0 in that blank space, you'd have 0.030. So you don't want to always have to write this out formally, this calculation. So you can just kind of learn that little trick. So 25 milliliters, this one, or excuse me, 10 milliliters. Oops, that's thinking of the next problem. 10 milliliters. You just move the decimal over 1, 2, 3, and it's going to equal 0.010 liters. So now you have both of the volumes converted to liters, which you need because molarity is in liters. Okay, so what we need to do, remember, we're not interested in molarity, we're interested in moles, we're interested in number of molecules. 1 NaOH for every 1 acid, okay? 1 NaOH, 1 acid. Or moles is simply molecules. It's just a big basket of molecules. So for every mole of NaOH, we need 1 mole of the acid, and when they're equal, then you're going to have your indicator's going to turn pink, and you'll know how what the concentration of the unknown. You'll know how many moles of the unknown acid you have. So let's calculate how many moles of the base we have. So we have this, I'm going to go ahead and just use this, and we have this many liters. Remember, this one is the base. I take that back. This one is the acid, the 30 milliliters, and this one down here is the base. So we're interested in the base right now. So it's 0.010 liters times this. Now, how do you know that? This is where you just got to get used to. You say, I couldn't see that that's what I was supposed to do. This is where you have to see that you line up your units so they cancel to give you what you want. What you're trying to find is how many moles of the base you have. Okay, but you have molarity, you have moles per liter. So you're going to multiply liters on the bottom, liters on the top, they cancel, and you end up with what you want. You want to know how many moles of the base you have. So 0.01 times 2 is going to equal 0.002 moles of NaOH. Okay? So that tells you basically how many molecules of NaOH you have, but we're talking in terms of moles, big bundles of molecules. Okay, so what you simply have to recognize is that 0.002 moles of NaOH, if it's going to neutralize with the acid, then you have to have 0.002 moles of the acid. So now you know how many moles of the acid that you have. It has to be the same as the number of moles of the base. They have to be equal for them to neutralize and for that solution to turn pink, for that indicator to go off and turn it pink. So this is how many moles of acid we have. But it doesn't ask us for that. It asks us for concentration. And just as over here with the base, concentration is in molarity. It's moles per liter. So we're going to take the number of moles of the acid right here. I'm going to move over here. 0.002 moles of acid. And I'm going to put it over the number of liters of acid, just like for base you did that here. And that right here is this number right here. That's the number of liters of the acid. That's the 30 milliliters. So now I have moles per liter. That's what I want. So now all we have to do is do the calculation. And that gives us 0.0, a bunch of sixes, we'll just call it 7. And it's a concentration, so it's a molarity. So you just use capital M, and that's your final answer. That's what it's asking for. The concentration of the unknown acid. That's what you just figured out. Okay, so let's go over this again. So first you had to do this busy work over here to convert milliliters to liters. That's not really part of the problem. I mean, it is, but you have to get into liters. But again, they could have made it easier and just given you liters, okay? But they didn't. Okay, so now you come over and you figure out how many moles, how many big bundles of molecules you have of the base. So it's moles per liter is molarity. You multiply that by the number of liters, that's this number, which you converted to liters. Liters cancels with liters, and you end up with moles of the base, and it's 0.002. For this to neutralize, you have to have that same number of moles of the acid. So those two have to be equal. So now we know how many moles of acid it took to neutralize this solution. So we come back over here, so I'm moving back over here. We take the moles of the acid, and it told us what the volume was, 30 milliliters, which we converted to 0.030 liters. So you just put moles of acid over liters, that's molarity, that's the concentration. Just like it was here, moles of NaOH over liters. Okay, you do the math, you get 0.067, and it's molar, that's the concentration. Okay, you're going to do the rest of them like that. I'll do a few more on the next video. We're already up to about 40 minutes, so let me cut this video and I'll finish this on the next video.